Hi, I'm Assaf. I'm going to talk about geospatial analytics, but just before we get into the actual topic, I just wanted to say that Big Things has been around for a while now, and I remember being a very young engineer and joining and looking up to many of the speakers in these talks, and it really made me want to be much better than I was. And so thank you for everybody who's been organizing this for ever since it began, and for everybody who's stepping in now and helping speakers in distress. Okay, so we're going to pick up where Chaim left off and talk about geospatial analytics, because that's really what we do here at Nexar. So just a little bit about the people who've been working on this. So I'm Assaf. I've been at Nexar for 5 years now. I've been working on all kinds of things, but recently I'm just transitioned to principal engineer, working on all kinds of infrastructure stuff. But previously, Avri and I together did this work of putting together this geospatial analytics layer. So let's just start with what Nexar does. So Nexar just crawls the physical world with vision data, with dash cams, and indexes it the same way search engines crawl the web. So our mission is to be that layer where you can ask a question about what's going on the road, and you can get an answer, whether that is a road blockage, whether that is slowdown on some roads, whether there's a parking spot near where you're driving. So you can think of all kinds of APIs where you can really make use of real-time data from the road. And we build that index using vision data captured by dash cams. So company's 7, almost 8 years old now. We've been growing steadily. The brand, the dashcam brand that we have is quite stable now. We have a significant market share of dashcams in the US. It's the #1. If you search for dashcams in the US on Google, Nexar is probably the first result you'd get. So we have almost 500,000 dashcams going on the roads, with a lot of data being captured every day. You can see that 4 trillion images collected up to today. That is, that's a very large number, and we don't just collect. You can extrapolate from that. We don't capture an image for every GPS sample we capture. So there are many more samples with the data that I'm about to talk about. So apart from crawling the physical world and assembling this digital twin of what's going on the road, there's also, we want to build the best dashcam in the world for our users, for our drivers. So there are all kinds of features we're building around about what your camera does when you're parked, like a sentry mode, live streaming from your camera if you want, all kinds of consumer-facing features. And of course, there's an enormous market for everything that's for road intelligence, basically. So starting from companies who build autonomous vehicles, or mapping providers, or automotive manufacturers like OEMs, they're all very interested in what's going on the road. They want to integrate with this data layer that could provide their offering, whatever that is, whether that's an AV or just a normal car, or their mapping service, really up-to-date data about the road. And there's also public sector, people who maintain our roads, maintain our streets. They want to know what's going on their roads, and the only way they have right now without Nexar is to physically pay people to drive around and actually look for things. So Nexar can really address that need, and use that digital twin to provide public sector with services like where there are construction sites, if if a city wants to enforce like their permits for contractors. Same goes for auto fleets and insurance companies. They can improve their services by having more intelligence about what's going on the road. Did I skip one? No. Okay, so, and to provide all these services, to build this digital twin, to run all this AI that takes these frames and detects these meaningful objects like traffic cones or parking spots or anything like that, that is a very data-intensive task. And the key for that is localized high-quality data. So, like, for detecting, let's take, for example, like traffic signs or traffic cones, as you see in this in the image. So if you want to detect construction sites, you need to be able to train your AI to detect these elements. And these elements may be different from place to place. That, like, if this is in Nevada, like Michigan may be using different kinds of cones, and your AI may be, oblivious to those kinds of cones. So you need, and the same goes for traffic signs. If I recently discovered that traffic lights in Japan are horizontal and not vertical, so I would assume an AI would also be kind of flustered by that. So you need very localized data and very high quality data and a lot of it. And in order to determine if we can provide this product for a specific customer, for a city, for an insurance company, for an AV, we need to know if in the specific area we have the data that we need to provide that service. So quantifying our supply is really the North Star of what we're doing. And the raw data isn't really helpful because it's basically physical measurements from GPS. So I'm oversimplifying here because there's more than just timestamp, latitude, and longitude. There may be some speed indicator, altitude, but not much more than that. And also, GPS data is messy. As you can see in the image on the left, the GPS is dashed, the raw GPS is dashed, and we overlay that with a map-matched trace. So you can do that mathematically, compute the most plausible path from a raw GPS. And raw GPS is messy it's just from reality because, the satellite may be, the signal may be going through, a thicker layer of the atmosphere, and that may be throwing your GPS antenna off. But even if GPS was perfect, even if you had that red line going through exactly where the streets go, that's not really meaningful when all you're getting in is that stuff, right? You need to be able to join that with some meaningful geospatial dimensions. So all the salient questions that business people are interested in, that customers are interested in, that users are interested in, are, they're framed in these. Is that the laser? Okay. So everything is framed in these geospatial dimensions, like how many residential road miles. So how do I know, from that raw GPS, what is a mile? What does residential mean here? People may be interested in only freeway data because they're interested in freeway, what's going on the freeway. Also, how do you define these things? We have, as humans, we have these general definitions. We know what Manhattan is or what Ohio is. But when you get down to the details, there are all sorts of quirks. If I have a query searching for data in Detroit, I discovered a few months ago that there's another Detroit, I think in Michigan, other than the big Detroit. So maybe it's in another state. But if you only search by the city name, you may get data from two different places. So we need a way to one-to-one identify this query to a specific shape on the map. What is a road segment? what is a tile of road? Sometimes a road segment isn't enough. Like if you're driving on a street, you want to know where exactly on the street you've been driving and how long you've spent there, because the data may, you might want to capture something that's in the middle of the way. We might want to provide a customer with a frame of a specific building. That's also a use case for what Nexar can do. So how do you do that? How do you, enrich and join and give meaning to that blob of GPS data? So this is what we're going to talk about. So I'm going to talk about some general DBT techniques for working with massive data. So I may repeat some of the stuff Chaim talked about, and I'm definitely repeating some of the stuff that's already online. But I hope this is helpful for anyone, even if they're not working with geospatial data. Next, we're going to talk about how DBT can help you work with geospatial data and how to optimize those for a modern data warehouse. And if we have time, I hope to speak about how to build trust in that data using DBT, how DBT can help us with that. So just a little bit about our stack. It's a pretty standard modern data stack with data coming in into Amazon S3 as a data lake and Parquet files or ORC files. We load the data into Snowflake in this case. Not all of our data is in Snowflake, but for the purposes of this talk, let's say that it is. And we process all the data with DBT, and then we can expose baked models for Looker. So the first technique I want to talk about is working in development. Chaim mentioned that with code spaces and so on. But just as to drill into the details here, you need to when you're working with DBT, one of the things that you configure is a profiles file in your home directory. And in that profiles file, you define basically your connection parameters to whatever data warehouse you're using. So we're using Snowflake, and I'm telling DBT to use these credentials and that account and which database and which schema. And notice that I'm using my own schema here because this is the dev target, and I've also defined the dev target as the default for the Nexar profile. Okay, so whenever I run DBT run without qualifying it with a specific target, I would run the DBT models against that schema. So, and you want that as your default because you don't want to work against production by mistake. Okay. Okay, so once you have that definition and you have this dev target, this will make sense. When you're developing a model in DBT, you can actually reference that target that's active at runtime. You can reference that in the model definition. So if you're materializing this table using the dev target, you can inject this conditional, this where clause, into the definition of the model. So if this is all Postgres rides, all rides coming in from a Postgres database, in production it would just be select star from that model and that's it, and whatever comes after that would be the same. But if I'm running against the dev target, this automatically would insert this filter so that I only process 3 days of data, because I don't want to work on the entire data set in dev. I want to iterate fast. So the next use for this dev environment, other than using partial data and also just not working in production like yourself, is that you can reset a dev environment when starting. It ties back to what Chaim mentioned about your own sandbox, your own space for working with the data. And this is actually in a clone. When you're running this operation, we wrote this, I think we took it off a discourse post on the DBT community, so it's not original to us. But when you run this operation, this is part of the DBT project for us. Whenever we start a new feature branch, we just run the same command. This is also in the README for our project, so any new developer can do this, and they're getting. And DBT would create this schema if it doesn't exist, their dev target schema, whatever is defined in the target dev. It would create that schema. It would, if it exists, it would drop it. And it would clone the production schema, public, as specified here, into that target schema. And this leans on Snowflake's zero copy cloning feature, so no data is actually being copied to the schema. It's only the references to those partitions under the hood. But to us, we can work against a full production schema here, but completely isolated from what's going on. So anything we mess up on our dev environment here, on this dev schema, sometimes 3 days of data isn't enough. So this is pretty fast. It took me 5 minutes here, and I bet I could speed that up if I used a different warehouse. But it's mostly just copying metadata over to the new schema. It just creates those tables and references the same partitions in production. So now we have a safe way to work in development. I want to talk about, now we're talking about like how to work with large tables. And the first thing I want to talk about is materialization. How do you, over time, when you're maintaining an active DBT model, how do you keep it up to date? So the default definition, if you don't configure anything in your model, DBT would basically destroy the existing table, or more accurately, it would create a temporary table of a completely new table with your data, and it would swap with the existing table and then drop the old one. So incremental is, any kind of incremental materialization is much more efficient because, especially if you're working with large amounts of data, you don't want to process the same data over and over again. And the way you do that is, I didn't include it here, the configuration. That's my bad. But basically, in the config for the model, I think I have it in one of the next slides. In the configuration for the model at the header, you just configure, I want to materialize this as incremental, and you need to add this logic about like this Jinja macro. So this starts an if statement here. If DBT is running in incremental mode, okay, so you can run this model either in incremental by default, or you can full refresh. You can specify that as a flag. But if you're running in incremental mode, it would, again, add this extra filter where you're selecting only the data. If you're selecting from this base table, you're selecting only the data that's loaded after the current maximum in this table. Okay, so this means like if you're going to maintain this, you need to remember you need to keep a column in this table that you're implementing that would be used for subsequent incremental runs. Okay, but once you have that, you can just select only the data in the base table that's been updated. So that's pretty simple to implement, and it's robust to updates of all kinds. So you can run this incremental update once a day. You can run it once a week, and if you run it once a week, it would go a week back because everything that's later than the max loaded date would be included in the materialization. And it's usually what I recommend for anyone going into like a large data set with DBT. And it really pairs well with manual clustering. So I'm going to talk about that in a bit, but like if you do manual clustering on a very large table and you do it right, then your incremental materializations would be very significantly accelerated. So a more advanced technique I found was a materialization strategy called insert by period. It's already implemented in the DBT utils package, which is also open source, and you can import into your project. But I had to make some adjustments to it was originally implemented for Redshift and optimized for Redshift, so I had to make some adjustments for Snowflake, at least at the time. But what this does is basically it's very good for data that's very cleanly partitioned by time. So if you have data that's bulk updated every day, and you know that there's no, and you can assume that there's no late arriving data. Okay, so nothing. If you process the data from yesterday, there's no new data that's going to come in for that day. After you do the materialization, then that is a very good strategy because this. Oh, I'm sorry, I put in the wrong code snippet here, but because this is the same as the last one. But what this does is it basically it chunks up the data in the base table in whatever you're selecting from. It chunks it up according to some column, and it only processes like every chunk at a time. So even if you want to backfill a large table, and you may be running a backfill for a very large table you're running a backfill for a year of data, and you might want to cut off that backfill at the midpoint, or maybe you just don't have enough resources for running like such a large query over the base table. So you might need to chunk up the data into bite-size pieces, and that's a really good strategy. We do use that for our largest tables, our highest throughput tables, and it's very. But the flip side for that is that you have to be sure that no data is going to come in late. So if any data is coming in late, you might have to either reprocess that, or it's very good for backfills if you're going way back in time, but it's sensitive to late arriving data. So I mentioned clustering keys and manual clustering. So this is where it plays out. So usually, if you're using Snowflake, probably I think BigQuery also, and not sure about Databricks, but they kind of partition the data automatically. They partition the data based on whatever is optimized, whatever is their internal implementation. You don't have to care about how the data is physically partitioned on disk with the data warehouse. But sometimes you do want that control, and you want to tell your data warehouse, I want to partition this data by operating system, and then operating system version, and then by when that ride started. So for this example, we're taking data from rides at Nexar, and we're partitioning that by operating system and date, whenever that started. Why is this useful? Because if my most demanding queries are either filtering or joining by any of those expressions, then what Snowflake can do, and this is true for Databricks as well, with Z ordering and so on. What Snowflake can do is the query optimizers, once this table is configured this way, the query optimizer can say, okay, if you're only interested in Android rides, I only need to scan these partitions on disk. Okay, so the disk scan, which is the most expensive part of most queries in a data warehouse, you can really prune that that query down. The data warehouse does. So you just need to configure, you just need to know your data, actually. You need to know which downstream models in DBT and also end user queries, how are they going to hit this table? If they're going to hit this table in a very kind of not in a very predictable way, then I would think twice about using manual clustering because it can also hurt you. But if it's very predictable, I always query this table. I always have a filter for a date because I never select for all dates in this table. Then it's really useful to use a cluster by and use a date here. Any questions so far? OK, so we've covered the general stuff about working with DBT and large tables. I'm going to go into geospatial stuff now. Are you sure that you don't have any questions about what I? OK. So now let's talk about geospatial data. So remember that ride trace I showed you. So one of the dimensions that we need to ask about, we need to know about, is how things are connected on the road, and what kind of road is this driver driving in? Okay, is this ride in a is this GPS sample on a motorway, or is it on a residential road? So we use OpenStreetMaps for defining what the road network is. It's a very well-known crowdsourced project. They provide, I think, there's even hourly updates you can consume from OpenStreetMaps, or even tighter than that. But once in a while we just download a full planet-sized dump of OpenStreetMaps. We use Spark to pre-process it into these different, kind of pull apart these different entities. So OpenStreetMaps has a pretty simple entity model, 3 different entities all in all. One is node, just indicating a point in space. Away, which is a sequence of points. And relations, which define like all of these roads are part of something. Or a way may be completely, a way doesn't have to be a road, actually. It can be a river. It can be a boundary around a building. So a way is just a sequence of points. And all of these entities are annotated with just key value tags. And so any kind of metadata can be extracted using, if you parse the tags part of the entity. So for example, there's a very important tag on the way entity, on some of the way entities. As I said, not all of them are roads. But those that are roads have this tag highway. And the value indicates what kind of road is it, whether it's a motorway, whether it's a residential or a service road or anything like that. And we can also figure out, like, a road is basically, if we say, OK, a road is represented as a OSM way, then we can break that down into segments, like source and destination, pairs of nodes. And we can compute the length of the entire way as the sum of the distance between those points. So haversine is just the snowflake function we use to compute the distance. It's just it's a well-known function for geodesic distance. So once we have that, I mentioned road type. We can then just ask questions about the map itself without even taking Nexar's data into account. This is just about the map itself. What is the distribution of like total road miles in different counties in north central Texas, this is just an example I worked on recently, what is the distribution of road types among each of those counties? So this is all based on OpenStreetMaps data, because like the total miles is just the sum of all those haversine distances, and the road type is the dimension we use to group by that data. So that's all around the topology of roads. I'm going to tie it all back in soon, so hang in with me. So now how do you address these places? Like I mentioned some question about how many miles in Ohio or how many road segments in Manhattan. So you can just use names. Like some data providers, they can enrich your data for you with country name or city name or anything like that. But we just because we've been burned in the past, we decided to do it right this time, and we used this repository called Who's On First, which is basically a big list of places. Any kind of place that has some human meaning. It's not necessarily a road, but it can be any kind of governmental geography, but it can also be like venues or anything like that. But we use it for the what's called administrative places, like countries, regions, counties, and localities, which is all kinds of cities and towns. So this is, if you go into Who's On First, they have like a search engine that you can search for different places. And this is the entry for New York, for example. And like this is really helpful, just having this shape instead of using just this bounding box. This is what we used in the past, just using a bounding box that's aligned with latitude and longitude, like 2 points on the grid. So having this detailed shape gives us much more accurate results, and we can also address different semantic layers of those places. So I can not only select for anything in New York, I can also break that down by borough. Okay, so we can group by, I want like the total number of drive miles for Manhattan, for the Bronx, for Queens, for Brooklyn, and Staten Island. Okay, having stable identifiers is very. I underestimated how important that is. Just having this ID that you don't have to rely on names. As I mentioned, there are multiple Detroits and there are also multiple Jerusalems. I don't think there's another Tel Aviv, but there may be. I know there's Tel Aviv Street in many places in Israel. So you don't want to use names because those are kind of messy and overloaded. And a stable identifier is just a lifesaver in this. Any kind of where you want to have a foreign key between tables, you don't want to be the name of a place. You want that to be just a single identifier. Of course, every place has a GeoJSON shape attached to it. Basically, what Who's On First is a bunch of Git repos with GeoJSON files. So all of the data in Who's On First, you can just clone a repo for, for the US, all the cities in the US, you can have a repo for that. And those are just GeoJSON files. And it also includes some really useful metadata for like population and hierarchy. So hierarchy, I mentioned boroughs in New York, or you can group data for every city in California or anything like that. And you can, using the population field, that's really useful because sometimes in our business we want to, I want to see a list of what's our coverage in the 10 most populous cities in Europe. Okay, so I don't want to provide a static list because that would be kind of laborious. And like you can just filter places by, okay, I want every city over 100,000 people. Just give me the numbers for that. That's really, like the data from who's on first is really useful for that. So, and what's tying all of that together is called H3. Has anybody here heard of H3? Anybody heard of S2? No? Okay, so they're all just grids of the world. So the idea here is that what Uber did, they had very similar problems to what we're having. Instead of doing these geospatial queries like point and polygon, I want to see if this driver drove through New York. So I would have to filter the drives for the GPS samples I have. I would have to filter that with a where clause of latitude, longitude point in polygon New York, right? And that computation of a filter is very expensive. It's much more expensive than an equality expression. So what Uber did here and what Google did before that with a different system called S2 is you just divide the world up to a grid. S2 or Google, they used square or rectangular or quadrilateral cells. And Uber used hexagons, but it's basically the same idea where you can define this grid at different levels of granularity. So at the global level, you can project the Earth as like this soccer ball of different hexagons, and every hexagon is a parent to 7 smaller hexagons. But you can see that it's not it's not 100% aligned. There's always a skew, but if you take this big one here and you dive into the smaller one here, then you can see that all the hexagons, like the smallest hexagons you see here, like this one, they most of them perfectly align with the largest one. So the skew between levels, it cancels out every 2 levels. Okay, so it's pretty consistent, and you can compute for a specific point on the Earth. You can compute the hexagon at every level you want, and you can also compute the hexagon for every like very granular hexagon. You can compute all the parents on top of it by just using bit operations. So you can just shift bits around, and you can get the higher level hexagons. Why is this useful? So what I forgot to mention about H3 is that every hexagon is a number. Okay? So every hexagon has an identifier, which is just an integer. Okay? So now every location, if you map every location in your system to a hexagon like that, now any kind of join or any kind of filter you have, you can do over integers, which is much, much more performant for any kind of computer, and especially data warehouses that have columnar storage. So integers are really if you drill down to the details, that's the key for why this is successful, why Uber went through the trouble of inventing this. So now H3 is basically the layer where we tie everything together. So we take all of the data we have from OpenStreetMaps, and we can compute for every node, every point on OpenStreetMaps, we can compute the H3 hexagon, the integer that it maps to, at any resolution, just using this Python library. So we do that using PySpark before we load the data into Snowflake. So we enrich the dump we take from OSM. We pass that through PySpark. We enrich it with its H3 metadata for every node in OpenStreetMaps, and that is what we load into Snowflake. Okay, and the same goes for places. So places, it's a bit more complex because it's not a single point. You're taking a shape, in space, and you want to fill it with polygons. And basically, if instead of computing whether a point is in this very complex polygon, you can compute whether the hexagon for what indicates a drive, whether that hexagon is equal to any of the hexagons that constitute California in this example. Okay? So this representation is a bit misleading because you would have to use the same level, like the same resolution. So you can't have hexagons like these big ones and these small ones and compare them. So you have to like drop them all down to the most granular level you have, and compare apples to apples there. But basically, you can instead of doing point and polygon filtering, you can do basically equality checks on a what's it called, like unnested data. You can take the data from California and just represent it as every row would represent a hexagon that is part of California. Okay, so that takes care of the metadata, what we need to enrich, the dimensions we want to add to the data. This is what we're actually recording. This is Nexar's data. So how do you enrich the map with H3? So I mentioned basically the same thing. Okay, so the same thing we do with OSM nodes, we can do to any kind of GPS point. But what we want before that is to kind of snap the data onto the OSM grid, the OSM road network, and then compute the hexagon for each GPS sample we have. Okay, so a GPS sample may be, if this is a road segment, a driver may be here, or they may be here, or they may be here. So we want to take and the GPS sample when they were here may be actually here. So the first step to do is bring that point over here to the actual road, to basically what you can interpolate from the OSM network, and then compute what the actual hexagon is where they drove. Okay? And if you combine a H3 hexagon at a specific resolution, we use resolution 12 by default, which is basically like I think an edge of a level 2. Oh, it's here. So I think it's around 9 meters last time I checked. But this is the just to give you a sense of scale here. So this is like 9 to 20 meters here, the edge of the hexagon. So we can locate driver locations down to that resolution. So now everything we have in these, every location data is represented as either integers or a set of integers which we can then unnest. And now what do you do with that? So, and DBT. So what we have with the data we load from that Spark thing where we enrich with H3. So you can see those in the green boxes here. This is from the DBT documentation site for our project. So we have who's on first metadata, no H3 there. This is a table representing like H3 hexagons for every place we're interested in on who's on first. So countries, states, cities, and so on. And for OpenStreetMaps, we have H3 data for every node here and every road segment. Okay? And from that, we can generate, DBT helps us kind of scalably generate these tables and test them that they're correct for like what are localities in everywhere. We want the hexagons for all localities we know about. Same goes for regions and counties, and also road segments. And from there on, if you skip ahead, we reach this hexeg table, which is basically what we use for all kinds of joins. Okay, so this combines, if you look at the definition for a hexeg here, this combines the locality of a hexagon. So a road segment may be 200 meters in length, and sometimes we want to know exactly where that driver is on that road segment. So the hexagon gives you that, and the road segment gives you directionality. It gives you the road type, gives you distance, and so on. So when you combine them, you get the best of both worlds, but it's a Cartesian product of all the hexagons and all the road segments. Any questions so far about what is a road hexeg? So this combines, I'm sorry, but the road hexeg table here also points, you can see by the way that it depends on who's on first data. So this table has not only every road segment and hexagon combination, it also maps each one of those to which city is it located in, which state is it in, and which county. And we can add any kind of layer we want to locate that place. So so just as an example of how we actually compute stuff using this geo layer. So once we have those tables, you can take, this is where we compute a rollup of daily GPS samples, daily rides, and daily users for every road segment. Okay, this doesn't actually include hexagons, but this is just a rollup of source node ID, destination ID, and down below, I didn't include it in the snippet, but there's a group by, so you can I'm sorry, this is the result after you group by. So once you have that rollup, you want to enrich it with all kinds of information about, let's say, places. So basically, this select, it takes that rollup I showed you just now, joins that with the road segment table over the source node ID and the destination node ID. And then you can join that road segment table to any kind of locality, region, county. So that's how you generate a rollup table that's ready for querying, because now I can query by, using this table, I can just select the county IDs I'm interested in and give me all the unique users in each county every day. Without having, so when we generate that table, no one that's using this model has to know anything about H3 or how we do things. They just need to know what to select for in these identifiers, and they can just group up. If I'm talking about analysts or any kind of like CTO, CEO, they don't need to think in terms of H3 or anything like that. Last thing I want to mention is DBT really helps us deal with UDFs consistently. So I mentioned layers in H3 where you might want to, take, you might want to represent California, which is a very large state. You don't want to represent it as like the tiniest hexagons, because then you would have, like if you take the whole world in those tiny hexagons, you have like 1.6 trillion of those. So you don't want that. And even at the state level in the US, that's not very helpful. So for states, we represent them as level 8, like resolution 8. And for cities, we take resolution 10 to represent like the polyfill of that shape. And the way we can traverse between those resolutions is using these UDFs. And as I mentioned, like all of the transitions between levels here, we just implemented them in SQL because Snowflake has these bitwise operations. So we just implemented like all these these bit operations to take this H3 index, which is an integer, and shift it left however many resolution, like the resolution that we want. And that's basically it. So we can compute like the parent. Like if I have a cell at level 12, I can compute its. I want to join it to the level 8. Like let's say I want to see which state this is in. So I basically just compute the level 8 hexagon for it using this operator, which is very fast. And then it's just an equality operator. Okay. These two for sanitizing these H3, because like it's the spec for H3 isn't definitive about non-significant bits. So this just zeroes out non-significant bits. And here we can parse like H3 addresses in hexadecimal form. This just parses them into integers in Snowflake. So that's kind of very inside baseball, but DBT really helps us, create those functions consistently and make sure that anything like that is maintained well and tested and so on. So these are all the things I've covered. I think we're out of time, are we? Okay. Yeah, so just to recap, we covered some general techniques about dealing with large data in DBT, with setting your own development workflow, using manual clustering for very large tables to optimize for fast, predictable query patterns, and materializing these large tables efficiently using either incremental or insert by period. If you start with incremental, you probably won't go wrong. If you see that it's really slow, consider using insert by period. And then specifically about geospatial data, just giving meaning, human level meaning to like a customer success manager here could ask me, okay, how many miles do we drive in San Francisco in a month? We can actually answer that using this data from Who's On First, and it would be accurate. I wouldn't have to, like, if you're working with any kind of, if you're working in a data team, you keep having to ask, like, what do you mean by, right? You have all these questions of, what do you mean by New York? What do you mean by miles? Or do you mean total miles or unique miles? So this makes that work all the more easier, really much easier. So we covered H3 and what hexegs are. We do fall back to geospatial functions in Snowflake. One question I was expecting to have from any of you was, wait, Snowflake has geospatial functions and BigQuery and Redshift had them for much longer. Why not just use those? Maybe you, like, those are geospatial functions which are compute expensive, like point in polygon. That's why we use H3. But at the time we developed them, Snowflake didn't really have those anyway. So we kind of, it forced us to do this better. But sometimes when the geo layer isn't really complete, there's a new location we didn't have time to include in that geo layer, then we do use sometimes the geospatial functions. We just use, we take a GeoJSON, cast it into a geography object in Snowflake and work with that. Yeah, that's all I have. So thank you. Yeah, I'm very happy to take questions. I think the question is, when do we get to go home? I'm happy. You can reach me at assaf@getnexar.com, or you can just grab me here if you want. Thank you. Thank you for listening.